Andy Kettle here once again from Servo Components and Systems here in the UK. Today I'm going to just run through a quick video showing you some of the differences you have in feedback devices on servo motors. Now here we have quite a large servo motor with a built-in encoder. It's robust, ideal for large machineries and ones that you can walk over. So not going to cause that much damage by stepping on it. We've got the encoder with the feedback and the power here, so we've got cables with the connectors. Now when you go down to smaller motors, quite often you need to add a kit encoder to it. Now here we've got a smaller motor with a incremental encoder, which is a 2009 incremental, giving us 8,000 steps per rev. Problem here is, because it's a smaller encoder, we've got to get the cables out somehow, and normally they're fly and lead and you've got to make your end up, which we can do for you, but not quite so robust. So ideal for machinery such as printers, scanners, desktop items and so on. Smaller machines, you wouldn't want to step on that. It wouldn't last very long. So what can you do if you want to go smaller but slightly more robust? So here we have another type of encoder, another kit encoder, but it's absolute, stainless steel cover, and we've got an M12 connector bringing out the encoder signal. It's absolute and it's 16-bit multi-turn, which gives us 65,000 revs that we can remember when we power down. And it's a 17-bit single turn resolution, which gives us around 131,000 pulses per rev. So you can see it's much higher resolution than the incremental types. The other advantage of this encoder, it's no hassle, no battery, and no maintenance. So it generates its own power, which is quite nice, and retains it. So this particular one is a Biss C, as I think I said, and we can interface that with our range of Copley drives. And in a moment I'll show you how we interface it to a BEL drive, but it could be any of the Copley range. So now I'm going to show you how we set that up in a drive. So what we've got here is an ElectroCraft motor. You can see here with the Absolute encoder on the back with the M12 connector and cable, and we made up a drawing which we do with all our supplies, so that we know what we've shipped and how it's connected. All the information you can find on the website. So it's a Copley BEL drive. It's a low voltage drive, and this is a low voltage motor. We've connected up the 3 phases. We've got a link here for safe torque off, but normally you'd link that into your safety circuit. We've got a serial key lead here going into the CME2 programming software, which we'll demonstrate to you in a moment. And so we should be all good to go. One final thing, most important thing, we've got it connected to a 24 volt supply. So there we are, that's the setup, and now we're going to go over to CME2. So here we are at the CME2 control desk. You'll see that it's actually on COM3. And the first thing we just need to do is just go into the setup and make sure we've got the settings correct for this particular combination. We have a Biss C motor feedback, so we've got that there. It's a rotary type. We haven't got any halls connected, don't need them with this Absolute encoder. We've got it set in CAN over Ethernet mode, but that's not important for this demonstration. If you want to change it, you click this and I'll do it so you can see. Just click through it and here you'll see you've got a whole number of feedback options, including the incremental, but we're going to stick with Biss C. We've got a 17-bit single turn, which gives us a 131072 counts per rev and 16 bits for revolution, so we can go 65,000 revs before we lose position or it rolls over. We've got an encoder filter here, which we can bring up errors if we get any noise or whatever. The brake setting and mode, position mode can be current, velocity or position, and the various operating modes. And then we've got our emulated feedback output, which we can produce from the drive. Okay, so we'll save those. Now we can go into the motor itself, and you'll see we've got the ECL motor, ElectroCraft motor, and that's the number of it. data you can get from the data sheet. And here again is the feedback if we need to change it, which we don't because we've done it all. One thing we need to do though is check the data sheet to see what order the data comes back in, and here you'll see we've got it set to position, status and alignment, but it could be any of these. And we know that the encoder can handle a 4 MHz data rate. Now if we click this button here, it will put in some starting data based on the parameters of the motor, and that will allow us to run the motor somewhat to allow us to start tuning it, etc. So we set the motor parameters up and the encoder, and we clicked the calculate button, which set the startup parameters for the PID loop. Now what we must do is go into the auto phase to make sure we can phase the motor windings with the encoder. And first of all, we need to move the motor in the direction we want to be positive. So normally it's positive is the clockwise as you look at the motor shaft, but it could be the other way around. If you had a gearbox, for instance, you might want it the other way around to make it easier later on. So now I'm going to click yes, next rather, and we bring up the motor wiring setup. So now I'm going to hit start. So let's just make sure that the wiring is set to match the UVW and the S1, S2, S3 feedback from the halls or from the encoder. And so now we've got it connected and configured correctly. We can hit yes and go to the next step. And now we will check that we can perform 1 rev of the motor, and we can match this counts per rev. That's just configuring the settings before it goes. And now we've got to observe physically that the motor has actually turned 1 rev. There we go, the motor's moving, as you'll see. And it confirmed that you've moved it 1 rev. Well, it did, because I watched it. And you'll see that the encoder counts match. It also confirms that it believes it's got 4 poles. Again, that matches. Then we hit next again, and this time we're going to do a feedback phase angle setup test. You'll see the motor will do a little shuffle backwards and forwards, which will be replicated on the screen by the red arrow. And eventually these 2 arrows will coincide, meaning that you've aligned it properly. There we are. That looks like it's done. And now we've finished. And now we can go in and look at the tuning. Now the tuning does allow you to do an auto tune on the current, but because we've set the default parameters, it will be pretty close, and we'll go and use the oscilloscope to show you that. Changing the plot to current, change the setup to commanded current, and then generate the waveform, and you'll see that it's pretty close, pretty good. So that's the current tuning done. We stop that and now go over to the velocity loop. We change the put that in auto setup. It'll change these values here for you. Hit start. And there you can see the velocity loop. Again, I've already tuned it. There are other videos on this channel showing you how you can actually tune it properly. Stop that. Go to position mode now. Commanded position. Now, the commanded position is your step change. Active load position is your feedback. I'm now going to add position, limited position. Now this takes into account your acceleration and deceleration profile as set here. And I'm also going to put in the following error, position following error. So now I'm going to run that. There we go. I'll stop it so we can just zoom in a bit. So if I zoom in here, you'll see that it's very close to our commanded position, the limited position. And if we look here, you'll see that we're pretty close to 0 there on the following error. We can tune it some more, but as I said, there's another video covering this in more detail. Okay, I hope you found this video of interest, and thank you for watching. More information on our YouTube channel or our website, so plenty more out there for you to see. Thanks very much. Bye-bye.